small reintroduction of myself. My name is Cheemalapatti. I work at Google and headquarters in California. I work on Earth Engine. I mainly work on imagery and geometry stuff there. Really excited to be here in India. Sort of a last notice trip, but got together some cool stuff to show you guys. Thanks to Ujjwal for the introduction to Earth Engine. So this presentation is just supposed to get you a closer look at integration with Earth Engine and Python. So I saw a whole bunch of hands raised when Ujjwal asked how many folks are familiar with Earth Engine. How many folks have actually done anything in Earth Engine? Like used the code editor? Wait, really? I saw some code editors over there. So I know it's at least more than 2. Has everyone signed up for Earth Engine before? Yes, so at least some of you have accounts. How many folks are interested in following along with a demo here today? Okay, so we're going to spend a couple of minutes signing people up. It's super fast. We'll get there. Okay, so we call this Earth Engine 104 Python API. I'll get started. So we just got this big presentation about what Earth Engine is. Just as a really small recap, Earth Engine is a collection of servers somewhere out there in California. And we are a combination of a large amount of the world's geospatial data, a large amount of compute, and finally, there's some API interface that connects you to that compute. So we're all about you give us what it is that you want to compute, and we'll send you back results. So this is another representation of that. Now, in terms of just what we're talking about in the sense of what methods that you have to communicate with us, traditionally, that has been the web API, which is the code editor, which is most folks' introduction to Earth Engine, and is generally the nicest way to interact with us. Why? Because it's really easy to have iterative development. So doing things a bit at a time, adding your results to the map, that is all really easy in the code editor. But we also have a Python API, which is just a different way of communicating with Earth Engine servers, and that gives you other opportunities outside of just the code editor. Sometimes you want to see your results elsewhere. You want to use it in QGIS, for example. Maybe you want to build a server-side application of your own, which uses Earth Engine's data to deliver to users in some other way. That isn't the code editor. So here, just another diagram showing the connection between the web API, the 2 ways that we have that we publish to communicate with it, both the JavaScript and Python API, and the different ways you can interact with that. So we can say JavaScript is the code editor, but with Python, you can go through command line shell, you can go through web application, you can go through Jupyter Notebooks, which we'll be working with today. Any questions about that? The last session was really free-flowing questions, so I'm happy to continue that trend. So there are some pros and cons to both methods of speaking with Earth Engine. Now, in JavaScript, it's easy. That's like the #1 thing. You just log into code.google.earthengine, and it works. Now, the trick is, there's limited customization. Everything that you do with Earth Engine kind of sits in that browser. There are ways to import and export your results, but in terms of real-time computation, getting data back live, that's non-trivial. Now, in Python, you can pull that data back, you can customize it, you can use Python libraries, you can plot things with ggplot, you can use whatever image processing libraries you have to modify the data that you get back, and generally there's a whole lot more power because you have the power of Python and the Python community to rely on to do other cool things. That being said, it's not as easy, so some assembly required. So some of the stuff that I want to try today, take Earth Engine data and use the burgeoning Python community, visualization tools to do something different, like use ggplot to plot data that I pull back from Earth Engine, use OpenCV to annotate a video that I download from Earth Engine, increase the possibilities for what it is you can do, how you can represent your data, how you can show visualizations to your users. Okay, so this is for reference. You don't have to go to any of these links right now, but just the different ways to get the Earth Engine Python API. If you use Conda, it's a system for reproducible Python environments for scientific computing. We're on PyPy, or pip install Earth Engine API, and there's our GitHub repository there if you want to look. And same difference, just a reference slide. Okay, so where are we going with this? So today we're going to be using Collab. It's free. Actually, before we do all that, can folks go to signup.earthengine.google.com? If you've never used Earth Engine before, this is the sign-up sheet. I'll go back. So let's see if I can show you. No. Sign. Now, this might redirect me somewhere. Okay, yeah, so there's a sign-up form here. It's instantaneous if you fill it in. So as soon as you fill it in, it'll work. You have to do it through the account that you're going to log into Earth Engine with. So, you know, for me, that's siteteams@google.com, but whatever it is Gmail account you use, it's going to ask you what you want to accomplish with Earth Engine. So you can just say in this case that you're at the C-SAG workshop. There's a word limit, so I think you have to put at least like 8 words in, but it's automatic, so don't worry too much about what that is. Yeah, so I've put together some visualizations of stuff using Python, and I'm just going to show those off, talk about them slowly, and if folks have questions about some of the stuff I'm doing, feel free to ask. Was everyone able to open the slideshow? I see a lot of people in there, so if you don't want to copy this big link, the URL for the slideshow is here. It's that bit.ly, and you can log in. Yeah, if you type that link in, it'll open this presentation. Oh, and by the way, if you want to know like whether or not that sign up succeeded, if you just type in code.google.earthengine.co.in, if it shows up, then we're good. So this is Collab. Collab is a online interactive, yeah. Oh yeah. Will this work? Okay. Is that good? Yeah. So Collab is a Google-hosted interactive Python environment. It's really nice for this because I can share it, and we can all run this example together, and you can edit it if you want, and all of that stuff. If when you open this, it might say open in sandbox right here. If it does, please click that. Otherwise, you can't run it. Now, for Collab, Google provides a free hosted virtual machine. You can connect to it. And that virtual machine has a Python 3 runtime, and it has a GPU, which is useful for later. Yeah, so see if that works. So I put this bit at the top. You can sign up. I think folks have already gotten that far, so I'm going to move on. So in terms of using the Earth Engine API, first things first, we actually have to install it. In Collab, once you've opened it for starting and connected to a runtime, each of these cells is runnable. So if I click the play button here, if this warning shows up, it says wasn't authored by Google. It was, so say run anyway. And that'll get started, and it'll work, because I tested this morning. Yeah. So we're all good? Okay. First step, every time we start a session with Earth Engine in Python, we have to authenticate as ourselves. So that's why we all just signed up. When you run that cell, it'll print out a URL that you have to go to, and it'll ask you to authenticate using an account. And you have to authenticate using the account that you signed up for Earth Engine with. So for me, that's my @Google. Shows a box which says allow access. And it prints out a code that you have to copy and paste into the box. So copy, let's go back. If you paste that in, press enter, the session is authorized. So everything that we do from now on is authenticated. That is all of the setup, I promise. Does anyone have any questions up until now? We're good. OK. And the last thing we did there, we called a command called Earth Engine upload image. We just asked for the help. All that does is verifies that we're actually logged in. And we are. So we're good. OK. So the rest of this notebook is just demonstrations of using Earth Engine. I'm going to start with, yeah, was that a question? No. So I'm going to start with just the basics. We talked about how Earth Engine does all of this computation in the cloud. This goes from the absolute trivial computation of printing hello world all the way up to computing global mosaics. And the reason for this is that Earth Engine represents computations as graphs. Someone asked earlier, how do I implement parallelization in my algorithms? One of the reasons why Earth Engine is able to parallelize computations so effectively is because it does not execute them sequentially. When you describe a computation, when you design an algorithm in Earth Engine, what you're doing is building a graph, very specifically a directed acyclic graph, which represents what it is that you're computing. Every time you type something in, you type in image.normalized difference, you're not actually computing anything at the time that you ran that command. What you're doing is constructing a graph, and that total graph, when you go to evaluate your results, goes to Google, and we evaluate that on our servers. Being able to parse, optimize, and shard that graph is how we achieve parallelization. And that's how we run your computations on thousands of computers in parallel. This is just a really trivial example of this. So actually, yeah, that's fine. So running the cell, I define a string in Earth Engine, and I print the string. This call .getInfo tells Earth Engine to evaluate what I sent it. So in Python, this is how we print results. In the code editor, you can just call print. We do that behind the scenes. In Python, you actually have to tell us to do it. This is another example, just to demonstrate that concept. If I take two Earth Engine numbers, if I add 1 and 2, I would expect 3 when I went to print the result. But instead, I get this. So that's the graph that I'm talking about. That process gets sent to Earth Engine, and we evaluate it and send it back. In order to actually get 3 back from us, you have to call GetInfo. So GetInfo tells us to evaluate that result. So now I actually want to use the Earth Engine API to show imagery, to do some animations, to produce visualizations. My favorite use of GIS technology is to show information in a way that is otherwise inaccessible. So most of this notebook is about visualizing the monsoons in India. To start, this one cell is just a bunch of constants that I'm going to use. It defines a bunch of image collections, a bunch of variables that I'm going to be using later. S2 imagery, digital elevation model, some India level boundaries that I uploaded into Earth Engine, and a couple of other image collections that I'm going to be using. So if you're familiar with Earth Engine, they should all be pretty familiar. We're just loading various feature and image collections. OK. So in the code editor, one of the nice ways to interact with Earth Engine is by displaying imagery on the map. Now, we can do the same thing in Python. It's just a little bit more groundwork to do it. There is a library called Folium that I just installed by running the cell. And Folium is a wrapper around an open source map client called Leaflet. And Leaflet and Folium work together, and we can display them on Collab notebooks like this. So if I take Folium, if I define a function to add something to a Folium map, and I define a bunch of imagery, I can display some results in Earth Engine. And I'll go back and explain what all of that stuff was, but I just kind of want to show the result first. So in the same way that we demonstrated on in the code editor, you can do this in Python as well. So displaying a map client, displaying an RGB scene, displaying a false color scene, displaying an NDVI scene. This is all also possible in Python. Now, I'll go back and explain a little bit of what I did. So Folium is a map client, like I said. Most map clients allow you to add tile layers. So a tile layer is defined as a series of XYZ tiles on a Mercator map. All we're doing here is asking Earth Engine to give us a map. We're formatting it in such a way that this client is capable of using it, and we're able to add it to the map. Very specifically, this computation is just asking for a single S2 scene. I'm taking S2, filtering it to a certain lat-long coordinate, which is 81.9, 16.6, asking for the first image, which has no clouds whatsoever, and producing a couple different visualizations. So the first is a visualization of red, green, and blue bands. The second is a visualization of false color, the infrared band, near-infrared band on Sentinel. And the third is a normalized difference band by using that normalized difference function. Any questions about that? Okay. All right, so I have a couple more cool visualizations, demonstrations of producing imagery and displaying it using Collab. So this first one is produced by taking a digital elevation model, layering a rendering of India's state boundaries on top of it, and getting a thumbnail. So this is different from, for example, displaying something on the map that we had done before. This is collecting a thumbnail directly from Earth Engine. So instead of getting tiles, I asked for a JPEG, which was 512 by 512, and I asked for it over a certain region that I defined up above. Any questions about that? No? Okay, so now we kind of have a nice visualization of India and its state boundaries. I want to show some cool information. So first thing, a cool feature of Earth Engine, you can create animations. So Ujjwal showed time-lapse earlier, which was done by taking a global mosaic of the world, cloud-free composite, and then rendering that year over year from 1986 using Landsat imagery. While we can't do anything as sophisticated as that in real time, we can still do something similar. We can take, let's say, Beer's imagery, daily imagery at, I'm not quite sure what resolution that is, probably 10 kilometer by 10 kilometer or something like that. But we can take a collection of that. Let's say we'll take a collection from July. Is that July? That's June. So the month of June, take all of the Beer's imagery over the month of June, which are daily scenes, and let's get a video of that. So this thing is an image collection. We're going to ask Earth Engine to compute a video, show me an animation of it. And very specifically, I'm going to ask for an animation of the red, green, and blue bands clipped to India. And this will take a couple seconds to load. Now, the way that we're doing this, we have to, first of all, load an image collection, right? So Beer's is the set of all Beer's imagery that we have. We can filter it to a region, which will filter it down to, I think, 31 images for that month. And then we're going to apply an algorithm to it. So we're going to tell Earth Engine to do a computation on that imagery in parallel. Now, this map function tells Earth Engine, for each frame in that image collection, evaluate this algorithm called Beer's frame. Now, Beer's frame takes that image, it applies a visualization to it. So in this case, Visualize will produce a RGB image in which 0 is mapped to black and 3000 is mapped to white. And it clips that image to just the boundary of India. And the image collection, we return a mosaic, which is a black boundary, followed by a DEM of India, followed by our visualization, that RGB clip mosaic, and then followed by the boundary of Indian states rendered in black. We just flatten all of those together into an image. And we run that algorithm for every single image there, and we produce this cool animation, which shows one of the early months of the monsoon as the clouds flow into India and the whole country turns, what's going on underneath becomes invisible. So if you want to take a look at all of the data sets available in Earth Engine, there's this nice website, and we have a list of all of the metadata and properties for each image collection. So if I take that Beers collection I was looking at surface reflectance, 501 kilometer, you can see that I have imagery from January 19th, 2012 up until today.
So that is like already available in the data set.
Yeah.
I'm asking through code, we have analyzed the range of data.
Right.
From 2000, maybe 2018 Jan to 2018 December.
Right.
In between, there is no like sequence data is not there. Like whatever the data is already existing, they are using it and they are showing it through video.
Yeah.
So I just want to know in between what are the data they have considered it for preparing for video.
This imagery is daily.
No, the output will be through the kind of video kind, right?
Yeah.
I just want to know which are the data
Oh,
that
I
are
see.
used for it.
So
Preparing.
where can I go back? So I filtered my collection to a certain date range. So here, before I did that mapping algorithm, I only asked for imagery between within June of 2018. So this animation is some 30 frames just of June. Oh, so you're saying like how can I show the date? Yes. Yeah, we'll get there. We'll get there. I have an example in which I actually show what date it is. But very specifically, this animation is just 30 frames of June, right? So there's another example in which Yeah. You want a legend. Yeah. Right. There's another example I have in which I add a legend. Okay. So this first frame was just a visualization of one data set, right? So above the clouds, we can see the clouds rolling in. So I have a second visualization, this time of KBDI. It's an index of soil moisture. And I want to see kind of underneath the clouds what's happening as the rains come in. So this is kind of the same idea once again. I am going to do that same kind of mapping over a different image collection. And I'm going to produce a visualization of how on the ground the rain's coming in and clears the drought in India. So this takes, again, the same couple of seconds to load. And I'm doing the same thing that I did last time. There's no legend on this image. There will be one in a later one. But it is 30 frames over the month of June. And I'm doing the same mapping where I map over an image collection. In this particular case, I'm mapping over an image collection called KBDI, which is produced by the University of Tokyo. It's once again a daily mosaic of the world. And here you can see, I guess you have to guess because I didn't throw a date on there. But you can guess that from the start of June up until the end of June, as the rains come in, there's more moisture in the soil. So this is a somewhat obvious result, but it's cool to see the animation of it, and we can see Earth Engine computing that in real time. You have any questions about that? Okay. All right. So in terms of, like, that's just showing imagery, that's showing some animations. Earth Engine can also churn numbers. So we can do something kind of trivial here. Let's say I want to know how much rain falls over India in every single month of the year, and I want to plot that. We can guess, based on observations over millennia, that the most amount of rain falls in July and the least amount of rain falls in January and December. In terms of computing that, right, so I can pull rainfall data that exists. In this case, I can pull chirps data, atmospheric precipitation. I can use Earth Engine to get an entire collection over a year, and I can ask it to reduce that collection over each month by summing every single pixel over India over every single day in every single month, and then getting the result, and then returning to me a collection that says, here's the total number of millimeters that fell in January, February, March, April, May, June, July, so forth. And that's a pretty small algorithm, all things considered. This is the totality of it. It starts with just taking a list. So defining a sequence from 1 to 12. This is just the months of the year. That produces a list from 1 to 12. I'm going to map it over an algorithm called dateRange. And what dateRange does, it takes a month number. It computes a start date, which in this case would be 2018, the month, the first day of that month. And it computes an end date, which is 1 month after that. So just as an example, if I were to give the number 1 to this function, it would produce a date range from January to February. And then 2 would be February to March, and so forth. Once I have a sequence of date ranges, which represent monthly slices, I map that again over another algorithm called chirps daily sum. So chirps takes that date range, it filters from the start to the end of that date range, and then it sums the imagery in that collection that gets returned. So as an example, if I were to take chirps and filter it from January to February, that would return 31 images. So you would get a daily image every day of precipitation in millimeters. If you sum it, you get 1 image back, which is the precipitation over the month, the total precipitation over the month. But it's an image, right? Earth Engine has a concept called reducers, which is applying some mathematical function to every single pixel in an image at a certain scale. So finally, now that I have an image, which is the sum of all of the precipitation over a month, I can ask Earth Engine to reduce it by taking the sum of all of those pixels over a region. And in this case, the region that I'm going to provide is the level 0 boundary of India, so the country boundary. And if I run this thing, I'm going to get an X and a Y. It's done, okay. And I'm going to plot it with Matplotlib. So here's a graph of that data. And that was pretty darn fast. So Earth Engine churned a couple of gigabytes of data, summed all of it, produced results, and gave me a nice visualization of that precipitation. And I verified, what I learned from Wikipedia, which is that the most rain falls in India sometime in July. Any questions about what I did there? No? Okay. So I have this final visualization. I have about 10 minutes left, so I'm going to go through this a little quick. But this is a story that I got from a conservation scientist here in India named Madhu, who you may or may not have met. He had this very compelling story of a bird called the pied cuckoo, which is said to migrate from south to north India as the monsoon rains arrive. And this is apparently an ancient observation, and one that's verifiable by visualization, right? So I was curious. Well, Madhu was curious, and so he had plotted rainfall data from chirps. He had made this really beautiful visualization of chirps on a day-to-day basis, and he had taken bird sighting data of this bird, which is available online as a data set. And he had uploaded that into Earth Engine, and he had visualized that along with the rains. And the observation that he was trying to confirm was, if I take sightings of the bird that were reported by the public, and if I take data available in Earth Engine, which is the CHIRPS dataset, and I put these two together, will I see that as the monsoon rains arrive, the bird is spotted in the north? So I tried to recreate his work. I did the same thing that he did. I downloaded data about these bird sightings from the eBird project, and they kindly provided shapefiles, or I think a CSV. They kindly provided a CSV of lat longs and the bird sightings in India. I took that, I uploaded it to Earth Engine to an asset that is owned by me called PiedCuckoo2, and this is just a demonstration that you can pull outside data into Earth Engine. And I have this big script which does a lot of work on this animation, and I'll explain it in a second, but I'll just show you the results first. Run that. Run that. So that's a sanity check. This is frame 1 of that video. Run that, which is going to ask me to do this. I'll go through this again in a second, but I'm running out of time in my presentation. So I downloaded the video to my Drive account. Don't do that. Don't do that. Do that. Okay, I'm going to go all the way to the end of this notebook because somebody asked me about adding a date to a video, and I did that, and I want to prove that I did that. So this is the result of that, right? So it's a whole lot of Earth Engine code, but here we have the date, right? So you can actually verify what time that I'm talking about. And this is a really nice free-flowing animation of atmospheric precipitation over India, and the red dots are sightings of this bird that I downloaded from online. And we can kind of confirm, just looking at this, that there's a resident population in the south in May, and as we go towards June and July, it becomes prevalent in the north. So yes, it's true. The pied cuckoo migrates north over time during the monsoon season. So I have a couple minutes. I can either explain that whole script or I can answer questions. Explain the script. Okay. So there's a bunch of stuff going on there. Let's go all the way back. All right. So I had a bunch of animations before, which was taking a collection and then mapping a visualization and then putting all of it together and returning it. Now, this is much of the same. It's just there's a bunch of massaging that I'm doing to this data to get this visualization. If you ever throw chirps on the screen, it's relatively noisy to animate. Rain obviously doesn't fall in the exact same place for multiple days in a row. So getting blobs like that is quite difficult. The technique that I'm using is I'm creating essentially what are frames. So on the first day of January, the frame is 3 days, January 1st, 2nd, and 3rd. The average rainfall of January 1st, 2nd, and 3rd, followed by 0 times the average of January 4th, 5th, and 6th. And then on January 2nd, it's 2/3 of 1, 2, and 3, and 1/3 of 4, 5, and 6. On January 3rd, it's 2/3 of 1, 2, and 3, and it's 1/3 of 1, 2, and 3, and 2/3 of 4, 5, and 6. Essentially, I'm interpolating between average frames. Does that make any sense to folks? It's a little bit hard to explain here in code, but I create 2 windows. I create a window of January 1, 2, and 3. I create a window of January 4, 5, and 6. And depending on what frame that I'm on, I'm going to use a fraction of those 2 windows. This is a nice way to interpolate in such a way that there's not a whole bunch of noise. Because I'm using averages, as I go through time, I get less of the first window and more of the second window, and the animation flows very nicely. There are a couple more techniques I'm using. In order to get nice blobs instead of kind of pixel dots everywhere, I'm using convolution. So I'm taking the input image, I'm convolving using a kernel of 7 pixels, a circle, so I get blobs instead of squares or something like that. And then in order to get that kind of histogram style look, I am converting that image into a summation of steps. So I'm taking everything, all the rainfall that is more than 0 millimeters, all the rainfall that's more than 5 millimeters, more than 10. The resulting image has pixel values between 0 and 5. 0 means there was no rainfall. 5 means there was more than 20 millimeters of rainfall on any given pixel. And finally, I'm taking my pied cuckoo data set and then just filtering it so that I only get the points that fall between the observation dates of when I'm starting, which is sometime in May, to the frame that I'm animating, which, depending on what frame I'm in the video, is some point in time. And I'm doing that same trick where I'm compositing all of these layers and returning it as an image. That was a lot of stuff. If you walk through it on your own, you might be able to internalize some of that a little easier. But are there any high-level questions about what I said?
The window
Yeah.
is a built-in function, or is it some other Python way?
Yeah, so the window is, it's not so complicated. I'm essentially computing some dates. So my start date is sometime in May. My end date is 3 days later. So window width is a number of 3. These are parameters that you can adjust to change this animation. And on this calculation, this divide, floor, multiply, just arranges things so that on frame 1, this returns January 1st. On frame 2, this returns January 1st. On frame 3, this returns January 1st. And then on frame 7, it returns January 3rd. So some clever math to enforce what I want. And you can take a look at that. We can explain it later. And some of this other stuff that I'm doing, we talked about real-time and batch. This computation that I'm doing here is too expensive to do in real time. So I asked Earth Engine to compute it on more machines. Batch has the advantage of allowing you to run a computation for up to 1 week. So in real time, we allot you 30 seconds. In batch, you can keep churning numbers for 1 week, at which point we decide that it probably wasn't going to finish anyway and terminate the operation. For certain things, that means you can churn a whole lot of data, especially operations that we can parallelize a lot. And as Googlers, I can throw several tens of thousands of machines on it. You can still throw a non-trivial amount of work. But here I'm taking my collection, instead of computing a video in real time, I'm using the Earth Engine batch system to ask Earth Engine to schedule this work. And I can run this as a task. Here is this nice method that polls to wait. If you happen to run this cell in your own notebook, it takes about 60 minutes for this to finish, because this is quite involved. But it will finish, and when it does, the script downloads it to your drive folder, and Future Cells copies it out. So it copies it into this notebook. I have copied it locally here. You can see in files. When it shows up, I have my Chirps Biz video. And you can download it from your drive or from this notebook or whatever. And everything else, this is using IPython to display a video in an interactive notebook. I don't have a whole lot to say about that. And this last bit, this frame thing for actually getting a legend and a frame and all of that, obviously nobody wants to be given a graph with no X or Y legend. You want to actually have some information about what you're looking at. In Python, you can do that kind of stuff. This is probably not the easiest way to do it in the world. I'm sure there's a better library out there for annotating a video, but I was short on time, and so I used what I knew. But this whole block is using OpenCV. It's a library for image processing. And based on what I know about my video, I'm adding a label to each frame. So I'm drawing a label onto each frame of the video, and I'm producing a new video, which is annotated. So this final output is OpenCV drawing a date onto each frame based on what I know the date is at each frame. And if I had more time, I would have also thrown in a legend about what the colors meant, but that kind of work is possible. It is incredibly difficult to force Earth Engine to put a legend on an image that it returns, because that's not part of the platform. But in a Python environment, you can use the libraries that are available to do it after the fact, right? So this is a demonstration of that. And I'm out of time for my talk, I think. So it's okay. Well, in any case, I have reached the end of my presentation. So does anyone have any questions? Yes. Yeah, there is. However, it's not in the library yet. So we have a Earth Engine REST API, which is capable of returning NumPy data. We have not incorporated that into the client libraries yet, but if that's something you're interested in, we can talk, and I can show you how to do it. It's possible, but not easy. I was showing all of this spatiotemporal data. Is it possible it's soil moisture data? Yeah. So that one of the animations I had shown earlier was called KBDI. It's an index of soil moisture. Yeah, so this data set is a representation of soil moisture.
So how is this calibrated in the field? Like, is it accurate? Because again, it's a satellite data, right? You have to do it accordingly in the ground control points where
Right.
the resolution has to be as well, the
So
validation.
it depends whether or not you want to trust this particular data in terms of whether or not it's accurate. But if you have your own data, so say that you've collected data yourself about soil moisture, even if it's not a raster, if it's just points or things like that, you can upload that into Earth Engine and use it. In Earth Engine, if you have your own data, assuming it's in GeoTIFF or shapefile format or CSV, you can upload that into Earth Engine in the same way, for example, that I uploaded that data set of bird sightings. Here, you can upload it yourself. So if you have a GeoTIFF, you can put it up. If it's geo-referenced, it'll work. These same kind of animations that I'm doing, you can do it with any data set. The same, reducing or large-scale computation. There's nothing special about our imagery other than the fact that we have it.
Interpolation. It does interpolation as well? Because I have a point vector data and I want to see the interpolation part, kriging part. The kriging, interpolations.
Right.
For the spatial, yeah.
Yeah, you can compute that. I mean, you can write an algorithm to compute anything you want, right? So if you want to do if you want to interpolate, you can write an algorithm which is capable of interpolating in the same way that I did. If you want to do a linear fit or do a harmonic analysis or anything like that, there are algorithms to do that. And if you want kind of more demonstrations of the capabilities of Earth Engine beyond the examples that I curated, let's see. There's a developer site for Earth Engine. Developers, where are we at? So we have this long list of curated examples for stuff that you can do. I've demonstrated a very small subset of all of these, but for each of these things, we have scripts, explanation of what those scripts are doing in a forum that you can digest at your own speed. And what you're asking about may also be up here. Yeah. So that's a really good resource too. Otherwise, I'll see you again after lunch. Thanks.